Okay, I'm just going to go over Basil J. Hiley's layman talk. He told me this talk was not for professionals when he gave it, but I'm not a professional, so it's the easiest talk to understand the concept.
Please forgive me if I what something's happening. Oh, all right.
So he calls himself BJ also, which is kind of cool. I hadn't noticed that before. But basically, we have he's focusing on Heisenberg's discovery about the fact that because atoms are quantized, then you have spectral lines that are not the space-time continuum. And so these spectral lines are called the transitional frequencies of the Ritz-Rydberg combination principle. So I'm just going to go over these highlights of his talk, and then you can always, I'll put the link in the video so you can watch the whole thing. But so to quote Basil, he says, and the rule that Heisenberg found, or Ritz-Rydberg, if you go from energy n to energy m, and these would be like the electron orbits, and you take the energy difference, it gives you a frequency. And that frequency is the same as the sum of the transition frequencies from there to there, which would be n to k, and k to m. And if you put that in the exponential as multiplication, because it's squared terms, that gives you the energy. You add the frequencies. And that's where Heisenberg did this. So essentially, they're just talking about logarithms where when you're multiplying, you're actually adding. So he goes on to explain this with the graph. So you have the amplitude as energy, but you have the phase of the amplitude is actually this transitional frequency that is an exponential. And then you have this imaginary number in the exponential. Because of that imaginary number, you get a noncommutative transitional time frequency. And that's the secret sauce of the non-locality. So Bohr figured out that the Ritz-Rydberg combination is based on frequency, but it was Heisenberg who figured out that because the energy is quadratic, therefore you can add the transitional frequencies based on this Ritz-Rydberg combination principle. But then, and that originated from the very first logarithmic equation in Western science, which is the perfect fifth plus the perfect fourth equals the octave. So you have 3/2 plus 4/3 equals 2/1. When obviously, if you do that as just algebraic arithmetic, that doesn't make any sense. But if you understand it as geometric magnitude, then what you're actually doing is you're saying the octave is the geometric mean squared, and the perfect fifth is the arithmetic mean of these ratios, and then the transitional frequencies, and then the perfect fourth is what would be the harmonic mean, which is again basically just a time reversed of the perfect fifth, and that's what makes it non-commutative. So okay, I don't think I'm missing the. I didn't pull out the one part of his talk. Let's see where he's 32. Let's see if I can find it here.
To give you a frequency, that frequency is the same as the sum of the transition from there to there and the transition from there to there. And we call that the Rydberg combination principle, because it works all the time. And if you put this in the exponential of multiplication, because it's squared terms that give you the energy, you add the frequencies. And that's why Heisenberg did this. Okay? And that's why it comes out time and time again. Okay, now what Bohm did was to turn this into a structure process. So you can either talk about Q going from, and Eleanor, can I try something? That frequency is the same as the CQ to R stupidity.
Yeah, here's the, okay. So here's where he's saying it's non-commutative, is that the transitional frequency is actually gets translated into position and momentum. So let me see if he explains that.
They're saying you know where the particle is, but you don't. But brilliant. Show what this corresponds diagonal elements, because we put food in, and I can't say what we do with the waste, but we remain the same. And the becoming is the process. Okay. Now you do that with the position, but you can also do the same thing with the momentum. But now we can't specify, okay? We can't specify P and Q at the same time because of this blasted Gromov business. And what Heisenberg, brilliant, showed was this corresponds to the fact that if you first operate with P and then operate with Q, it's not the same as first operating with Q and then with P. And what he showed was that area, because it only goes down to H bar, the difference between these two is equal to H bar. Forget about the R.
So the H bar is that Planck's constant, which you can think of as the average energy of light based on frequency. So that's what brings it back to frequency, is when you have the H bar, all of a sudden you're dealing in frequency again, and then you're converting it back to momentum and position.
Okay, so now you guys can go and pass any paper in quantum mechanics. Well, almost. Okay, now then, what is the uncertainty principle saying? They're saying you know where the particle is, but you don't know how fast it's going, or you know how fast it's going, but you don't know where it is. Okay, we're but stupid people. But I can assure you the atom knows exactly where it's going. It doesn't have a lack of knowledge. It's doing what comes naturally. Therefore, this is the tremendous dilemma that people get when they're looking at quantum mechanics. Is the uncertainty due to our stupidity, or is there an intrinsic uncertainty in nature? Okay, so and those two sentences have been translated into cubing diagonal, if you know where.
So if you look at this, this is essentially, this image right here is essentially the future and the past overlapping, and that's why you get these like Venn diagrams.
It is, or cubing diagonal, if you know where it is. Now then, how are we going to talk about movement? Remember, David Bohm actually said it's enfolding and unfolding. Well, suppose we have Q being diagonal at I, and then these terms get shuffled around, and then it's diagonalized again. In other words, there's a process which is lost in this operation, in this mathematics that we're using. The process that's lost is the shuffling. And the Bohm thing is saying, no, I can talk about, look, this says I can talk about, Bohm tells me the momentum is at the point, but the momentum must be defined in this way. So what Bohm is doing, he's saying, I'm going to assume that the P's and Q's are well defined, but the process of going, the actual unfolding process, is that it folds, unfolds, etc. Okay, so here's the shuffling is, you shuffle the matrices around, there's some very complicated process going on there. And it's not, we don't know what's going on there, but the whole point is, we can do lots of things to find out what is going on there. So it's very interesting, why did Heisenberg actually write this RE to the IS? You'll see RE to the IS is the signature of everything that David Bohm did. If in doubt, if it's an operator, write it as an amplitude with a phase. And then what Heisenberg did was to say, let me call that phase frequency. Now why? Because atoms are quantized. And we have these spectral lines rather than the continuum. And then the rule that they found was that if you go from E, sorry, I can't see it at the moment because I can't see it, it's EN, I can read it, don't worry. I've got your pictures over the top of me. EN to EN, take the energy difference and give you a frequency. That frequency is the same as the sum of the transition from there to there and the transition from there to there. And we call that the Rydberg combination principle because it works all the time. And if you put this in the exponential of multiplication, because it's squared terms that give you the energy, you add the frequency. And that's why Heisenberg did this. Okay, and that's why it comes out time and time again. Okay, now what Bohm did was to turn this into a structure process. So you can either talk about Q going from end to end, or you can talk about it going intermediate state. So in fact, the actual motion, you have to sum over all these.
Okay, so essentially then the problem is when you translate that frequency and time back into energy as amplitude, the Bohr and Schrodinger method just assume it's statistical, and so you get this statistical average for amplitude. But the whole point of David Bohm and Basil J. Hiley is that you have this deeper non-commutative process of the transitional frequencies, and this is also Alon Kahn is pointing this out also, and that this process is going on before space-time exists. And so they just call it an algebraic structure as that creates the phase space. And so the problem is that when Feynman, he was just trying to maintain the calculus of the space-time continuum. So he said that the path is still continuous, but it doesn't have derivatives anymore. And then he said that you have to, because you get this infinity due to the squaring as a singularity, then he said you have to change the rest mass as renormalization. And so Basil J. Hiley is pointing out why that is wrong.
So the actual underlying process that's going on is more like a fractal. And now you see where the ambiguity is coming in, where your creativity might be coming in. So this is just a statistical average of all these underlying.
I'm just going to skip ahead
Go away, horrible man. The complex conjugate Schrodinger equation. And I felt very clever when I did this, because I invented it all myself. And then I was reading Paul Dirac's paper in 1930. He actually had exactly the same.
When he said horrible man, he was referring to
and he actually talks about
Pascual Jordan, who basically, Jordan discovered this non-commutativity, but since he was part of the Nazis, he was in the SA, which is basically like the brown shirts, and so that's why he's saying, he was a horrible man, so his science got covered up.
In his book, The Principles of Quantum Theory. He actually has the Bohm theory in his book, Principles of Quantum Theory, in 1947. And I think David got it from there.
So basically, he's pointing out that David Bohm actually probably got this idea of the quantum potential from Paul Dirac.
So, whether that helps or not, I don't know, but it's not pulled out of the air. Then yes, this polar decomposition is appearing again. And if you write it in the modern word, I'd like to call this the brown Hiley cartouche, if I may, because we tried to publish this equation, and the Phys were not very interested because they didn't understand what we were doing. It's a trouble with referees. But this equation is very important because what it enables one to do is to take Bohm's ideas and to deal with spin, and also to deal with relativity. You'll see in a lot of the elementary discussions of the Bohm theory, they can't do relativity.
I don't know if I've read this paper, Schrodinger Revisited, and he's saying that the referees did not understand what they were trying to say, and that's the problem with trying to get published in peer-reviewed papers, is that if you have this new idea, then they don't know what to do with it because they don't understand it.
I was going to say something beginning with B then, but I've checked myself. We can do something, and this comes from these two equations, and this is I've learned something. And this is the commutator that we saw, the order with the difference. And this is called a Jordan product. And I don't think Jordan doesn't get mentioned very often. And there's a problem here, a political problem, because Jordan actually was in the SA, not the SS, but in the SA. And I'll leave that just to that comment. Okay, now how do we get back to the paths again? Well, what we do is we say, okay, it's unfolds, enfolds, unfolds, enfolds. And this is Dirac speaking now, it's not me, not David. So we can regard, he says, it looks like a trajectory, and thus makes quantum mechanics more closely resemble classical physics. That was in 1945. But then, and Feynman saw what Dirac had written and said, all right, let me take the exponential again of this thing. And then, because Bohm is the ratio of this thing over time, it's essentially the speed multiplied by the mass. And then remember the story I started with? Where do you put, if you go to the limit, where do you possible momentum, possible kinks in those paths? So what we're doing is averaging over many paths.
I'm skipping ahead because I'm trying to focus on the solution. But basically, he's saying that both Feynman and Dirac were wrong because they were ignoring that you have to use Planck's constant squared, because when you focus on the kinetic energy, and when you use Planck's constant squared, then you have to use the quantum potential. And so what Feynman is missing here is the quantum potential. But de Broglie in 1960 already realized that the quantum potential makes it look like as if the mass has changed. And so de Broglie already knew that Feynman was wrong in 1960, but of course they attacked de Broglie.
Classical rule two. Value you find here is the kinetic energy and the quantum potential energy. You just can't get away from it. It's there. And the reason why I've got Rob's name on here is because we are designing an experiment to show these kinks in the trajectories.
So when he says they've designed the experiment, he goes on, he explains the experiment more in this talk, but what happened is because of the pandemic, they were not able to do the experiment because the lab got shut down, and then they ended up losing their funding because it was like a time window for the grant money, and so it had to get spent on other stuff or whatever.
Okay, so just let me summarize. We've got this uncertainty, this ambiguity, giving rise to a curve which is an ensemble average. So here's the zigzag. Now, Alan, you see we've got the freedom in there to be creative. But what becomes determined is the average of these individual trajectories. And those averages are what is known as the bump trajectories. But they come from this unfolding underlying process. It averages over a lot of them. And now I'm sorry, folks, for people who find mathematics rather challenging. Let me give you my artist's impression of what's going on. This process here is very much like representing the movement as an impressionist painting. You don't have to draw straight lines. And this is, I'm sorry, folks, whoever wants to believe in Feynman mechanics, they don't have my blessing. Because what it is.
So he's saying that what happened is that because the momentum is deterministic, this got called Bohmian mechanics. But even David Bohm said, no, it's not mechanics because it's this underlying non-local noncommutative process that's actually an active information that he'll go into.
It's essentially an railway. Chris got very angry with me for saying that the other day. Okay, can I now? Yep, that's right. Can I now bring it to a close? I think I've now shown Alan why I couldn't answer your question in 3 words. Because there is a deeper underlying structure, not only a structure in words, but a structure we can actually bring out and discuss in mathematical terms. Okay, so let's have a look at the overarching philosophy. What I'm saying is there is a deeper structure which gives rise to a non-commutative, and I'm bringing in a technical term, phase space. Phase space means talking in terms of momentum and position. A phase space, it's a dynamical geometry. And in this context, not all orders can be made explicit at the same time. And I use this lovely psychology gestalt, which you probably most of you know. I can't see the audience. Usually what I say is, do you see the old lady or the young lady in that drawing? And it's usually 50-50. And I always think there's something wrong with me because the first one that strikes me is the old lady. And all I want to see is the beautiful young lady. Can you see it? I hope everybody can see it. Here's the mouth of the old lady. Here's the chin of the young lady looking that way. Okay. But now it's not just a question of perceiving, but the Royal algebra, which I didn't have time to mention except in the last slide, shows you that what you do is you take all the structure in X and you transform it all over the momentum space and vice versa. In other words, the whole process is a non-local process from the start. And if you guys are worried about non-locality, action of the distance, this is not action of the distance. It is the process itself cannot be described in local terms. And I like to exaggerate things by saying the quantum processes are not going on in space-time. I'm demonstrating all the effects in space-time, but they're not going on in space-time. They're going on in this dynamical structure, which refuses to be pinned down. I can pin them down to a degree when I use the algebraic way of doing it, but then I have to project out shadow manifolds. This is my X position space. This is my momentum space. Remember those 2 pictures earlier on. And if I can neglect the quantum potential, voila, we arrive at the classical world. So that is just.
So when he says if you can neglect the quantum potential, in terms of biology, you can maintain that quantum potential as the non-commutativity, and that's what the Neigong is as quantum biology. Is that, and he even points this out. He says that in quantum biology it's been misunderstood because they're assuming you have to have this collapse of the wave function, when in fact he's proven that the Schrodinger wave function is the wrong algorithm to use because it ignores this quantum potential that's inherent to the mathematics. Let's go back to the very beginning.
no, there's not. There's this symbol, this symbol. They knew what those symbols meant. So my mathematics is essentially the following. I've got the Schrödinger cartouche, because when I see that, I immediately see a whole structure that I've learnt, which goes under the name of Schrödinger picture. And then I see this equation here. Can you see my cursor moving? Okay, good. Then I say, oh, that's bone 52. And that was the one that was called hidden variables. There's nothing hidden in it at all. The mathematical symbols come directly from the Schrödinger equation simply by writing this in terms of two real fields, R and S. So instead of talking about the strange wave function, what we talk about are two components, R and S, and treat them as something real. Okay, and then this equation is trivial. It's simply the conservation of energy. We have the kinetic energy here, we have the classical potential energy here, and this term appears by putting that in the Schrödinger equation. So mathematically, this is exactly the same content as that. So we're not doing anything new, but by doing it this way, we're looking at it in terms of conservation of energy, and there's another equation which you don't have to worry about, is the conservation of probability. And that's the only...
So what he doesn't get into is that he does say that there's like an extra squiggle in the physics. Let's see, is he have that before? He's talking about Newton. He talks about Newton, and he basically says Newton is wrong too, because there's this extra
general relativity point of view, trying to do the same things, quasi-gravity. Unfortunately, both of us have failed on that task, but it's been a lovely journey. Okay, so what I want to do in this talk is to try and explain the mathematics that lie, the ideas in the mathematics that lie behind the structure process idea. And one of the things is, what I keep emphasizing probably, is the word algebra. And I think David Bones, nice to remember David Bones just here, he said to me, I don't know around the world, but we have a snake called an adder in this country. I don't know whether it has the same name elsewhere. But David said to me, how do you turn an adder into an algebra? And I said, I don't know. He said, oh, go and tell it to multiply. The whole point about an algebra is that there are two things you do. You can either add things, or you can multiply things. And that's all you can do. And from that, magic appears. Okay, and so what I've been looking at in my professional background is these ideas of orthogonal symplectic triple algebras and geometric algebras. And, hey man, you guys, those who want to know about them, good. Those who don't want to know about them, good. I'm not going to go into the details, but I want to give you some idea of how they come about. This is exactly the same content as that. Read with their thinking. Okay. I'm not trying to make fun of them, but I had a great respect. I remember meeting John. He came into my room at Berkeley College, and we had a good old chat about nonlocality. Anyway, but he published, when we were talking about which way experiments, this is what quantum mechanics is. We know there's a source where our particles coming from the tail, and we know our detectors go tick. So they're picking. Whereas Bone was saying, look, either it goes this way, or it goes that way. What's the problem? And then, as Chris, the two Chris's uncle were responsible for this early on in the 70s, we produced this, and this is what John Bell said, this is possible. This is possible. Just recently, I've been talking to Teacher Zay, I had to stop exchanging email because he said, it's meaningless. And I'm sorry, I want to know what it means. And then, but of course, we couldn't do any experiments. We didn't know how to do experiments to find these damn fringes doing this. And then, my dear friend Ephraim Steinberg from Toronto, 2011, this came out. Okay, it's a stretch of the imagination, but I can assure you when you do experimental physics, if you get something looking like a theory, you want to go on and find out something deeper about it. But he was using light. And so our idea was to use particles. Now, I think this is beautiful. I don't know whether Chris showed it, but this is the quantum potential. You can actually see it. And you can see it, you can feel it almost. Because here are the two slits in the background. Look at this. What is this towering inferno? The council flats. No. Okay. And the particles come along here, and they go along this corresponds to particles going along there. And every time a particle hits this dip, the rate of change of the potential gives you a force, and it flips across. And what the Toronto people were saying, you can actually see these gaps. Okay. But that is with light on. This is the coming up to the barrier, the particles are moving up toward times along here. So they're moving up toward, it doesn't even get to the barrier and it bounces off. And what are you, Alan, worrying about decay? Somebody asked me a question about decay. Well, there it is, look. The particle sits around in there, depending upon which, and then suddenly something will come through. That is decay. Even in this model, you can't control the initial conditions. There's no experiment we can do which will give me a particle with an exact position and exact momentum. This is where the ambiguity that I was talking about comes in. Okay, are you sure the real world behaves like this, BJ? Well, I want to show you, we've been doing some experiments on argon atoms. And these are argon atoms, by the way, striking our screen. We've taken a photograph of them. But look what happens. So what we're finding is that we get the interference fringes as a statistical average over individual events. Okay, well, how do we do this? Well, we use this gigantic piece of apparatus. We put in our argon gas there, we excite, this is all in a vacuum, by the way. Vacuum almost up to space standards. And then we get the atoms going through there, and then we catch them with tweezers. Okay, it's not the tweezers you pull your hair out with, it's tweezers which are made out of lasers. Amazing. And you can catch them there, and then switch the laser off, and hopefully they will drop. And that's what you're seeing on those photographs. Now let me show you the apparatus. How about this? This is one end of it. This here, that's what we're limitedly working with. Here is the cooler, here are the pumps. Well, hang on, there's more. Here is an extension. The gas bottle is right at the end here. So this is the apparatus. He's the pilot, Joe Morley. Peter Edmonds was the man who originally built this whole thing. And you'll see a couple of guys sort of trying to get in on the act. One of them's Bob Callaghan, and, well, you know the other one is. They don't like us in experimental domain theoreticians. We always make things go wrong. Okay, so here we have this is now putting these bits together, the source, which gets trapped in here, which we then release so that it goes through the two slits and produces the effect. Now, I did have a lovely movie, but it doesn't work anymore. This one works. Yeah, okay, and then the reason I'm doing this is because I can actually measure the speed of the particles starting from the source here and ending up on the screen. And I can do that with this diagram. Here are the particles arriving, time at the bottom here. Here are the particles arriving at the screen. This is the light source, because when we get these things excited, you have to have them in excited states. Light is emitted, so we take the light, gets there in no time at all, the speed so quick we don't have to worry about it. And then that enables us to measure the distance it travels and the time when we see the difference between those two signals. Okay, so we know something is traveling between the source and the sink. And I refuse to leave it as a blank in the way the Copenhagen is. Okay, so what can I say anything? Well, go back to Zeno's paradox. His paradox is very simply, how can it be at a point x and yet move with a speed at that point x? How can it be at x and moving at x at the same time? Okay, now how do we measure speed? Well, we say the start, the finishing distance, and we measure the time it takes to travel that. And then we go to the limit and squeeze, because we're going down to very small. It's not like a car. We can't squeeze a car down to 10 to the minus 8 centimeters, even if you hit the brick wall. Okay, so then the question is, at what point? Is it at x1? Is it at x2? Or is it at some point in between? And what classical mechanics says is, the speed is the take a midpoint, and this is continuous. It's called the derivative. This speed is continuous. And that's Newton's first law of motion. For people who live in Finland, they know all about first law of motion on the ice. Right. But what Chris showed was that this actually bends here. So why is it bending? Why have we got this thing suddenly bending? Is it got a force there? So that usually what it is.
So this bending is what Hiley calls a new quality. What does he call it? An informational potential, a formative causality, the mathematical structure of the quantum potential. It contains information about the experimental environment, about whether it's one slit, two slit, whether it's diffraction grading, etc., etc. It's encoded in this extra energy, this new quality of energy, the quantum potential energy. You actually take the quantum potential energy from the classical kinetic energy. So this is what he's talking about right here, is that
I think if you want to move it off the straight line. No.
It's a new
energy that comes into play. So there's something
this is a new force that's
now
been
I'm going to introduce
discovered.
something which I think is new to most people. And that is known as Gronov's no squeezing theorem.
And when he
And
says
it's
it's from this
1985 that it was
magnetic
proved. Although when I talk to my high energy colleagues at UCL, oh, we know that. We don't call it that theorem. They call it, they're trying to get something with their beams and it doesn't work. What Gronov says that if you get a dense set of particles coming out of an orifice, you find that under Hamilton's equations of motion, you end up with a beam which has the same area. And what this is the symplectic canal, as my friend Maurice de Gosson says. You can't squeeze that sphere into a long, narrow distribution to get it through the eye of the needle. So you have to take that, and this is very important for us, to realize that there's this no squeezing theorem. Now, if we're using process, we can think about Hamilton's equations of motion as a flow from this region to that region. So we're thinking about flows now. Not particles, but just flows. And the flow we can get we can generate it from a function which is classical action, doesn't matter about that. And it gives you the Bohm momentum. And if you go back to the equation that I did for the Bohm Cartesian, you'll see that this is the momentum that appears in the second term to give you the kinetic energy, and this is the first term, which is the total energy. So it comes out of this flow. So we're actually talking about the process of flow. We do this classically, and we get this equation, but there's no quantum potential there. The only difference between the classical world in this picture and the quantum world is the appearance of that quantum potential. Okay, so let me just summarize the classical. But what we do now in quantum mechanics, we change this S from the action. Don't ask me what the action means because I have no physical picture of it at all. I don't even know what called action. But that's what they use. But it now becomes a phase. And I know what the phase is, because the phase is, if you have the background there, then you have these constant phase surfaces. And I think Chris did actually mention that in his presentation last time. Okay, now then. One of the things that we're going to notice is the phase always appears in this, it appears upstairs. I'm sorry, those people who don't know mathematics, just take a picture. I'm trying to get across. It's upstairs. And what we're doing is we're lifting.
So when he says upstairs, he means exponential. The phase is it's the energy from the frequency that's in the exponential. It's the phase of the amplitude is the frequency.
Classical motion to get the quantum motion out. And the lifting means turning that into this exponent, into the phase. Now, this is mathematicians did this, and I don't pretend to be a mathematician there. Turn it upside down, and you'll see the classical motion is on top of this deeper underlying process, which requires 2 points to talk about it, not 1 point to talk about it.
So basically, you have this extra force that's hidden in the classical motion because of this kinetic energy that has to conserve the area from that squeezing theorem, the Gromov's squeezing theorem.
And that 2 points is what I meant by this ambiguity. And so I can now bring out a very simple picture. Gromov's sphere, flow to Gromov's sphere. In classical physics, you can take that sphere and put it equal to a point. In quantum mechanics, you cannot do that. Okay, now then.
So in quantum mechanics, because it's based on the discrete spectral lines with using the Planck's constant, then you get that inherent non-commutativity from the time and frequency that then is converted into the energy of the particle and the location of the particle.
We're talking about trajectories, and in the Feynman approach, he talks about trajectories as well. We talk about paths. So let me do what Chris was doing. He first of all says these flow lines go straight. Oops, sorry about that. I touched something I should have done. I've got these flow lines, and when there's no obstacles in the way, box 1 goes into box 1, box 2 goes into box, and so on. When I put this slit in the way, I suddenly find box 3 goes into box 1. As the particle coming out of this box ends up in this box here. But this is just the wave function. This is just the wave function. It's the receptacle in which we put these objects when they finish. And we measure them. That's why we're worried about measuring the wave function. But they don't collapse it because we want to know about this. We want to know what's going on between. And the way the physicists do it is just collect all these together in an array. What's happening? I know how to get rid of it. I'm sorry. I'm learning.
So by using the matrices, you're not dependent on this, what they call the quantum measurement problem, which would be what's happening right here. In normal quantum physics, they just turn this into a statistical black box.
The technology, I'm driving this technology along as I go and learning. Okay? So this means I've just got one path, and now the difference between these two is just noughts now. Oh, 3 appears down the diagonal, 3, 3, because it goes straight through. But the other ones that are deflected suddenly appear in other positions.
So the ones that go straight through are zeros. And then the one you can actually then measure the quantum potential as this deflection. And that's what he was showing before, is that's what the Bohmian model does, is it actually shows you what's happening that causes this wave distribution. And it's not just statistical. It's actually due to this deeper non-commutative matrices of the transitional frequencies.
So this is the operator formalism of quantum mechanics, which you can see what it means in a couple of seconds. It's just describing all the processes together, and that's why we're getting averages. And if we add these paths up, that's Feynman's path integral approach. And the only reason why I got this slide up is because the process. Shush. Sorry, how do I get back again? It just goes on and on and on. I've made a mistake. I'm getting excited here, Eleanor.
Use the arrow to the left, Basil, then it goes back up.
Which arrow to the left? Which arrow to the left? Oh, you mean, sorry.
One.
No, it's still going. Oh, yes, it does. Thank you. Oh, I'm glad somebody knows what they're talking about. Right. So what I want here is I want you to note that now the diagonal is being, because it goes from one box to the same box. And we are diagonal elements because we put food in, and I can't say what we do with the waste, but we remain the same. And the becoming is the process. Okay. Now you do that with the position, but you can also do the same thing with the momentum. But now we can't specify, okay? We can't specify P and Q at the same time because of this blasted Gromov business. And what Heisenberg, brilliant, showed was this corresponds to the fact that if you first operate with P and then operate with Q, it's not the same as first operating with Q and then with P. And what he showed was that area, because it only goes down to H bar, the difference between these two is equal to H bar. Forget about the other, not important. Okay? So now you guys can go and pass any paper in quantum mechanics. Well, almost. Okay, now then, what is the uncertainty principle saying? They're saying you know where the particle is, but you don't know how fast it's going, or you know how fast it's going, but you don't know where it is. Okay, we're just stupid people. But I can assure you the Argon atom knows exactly where it's going. It doesn't have a lot of knowledge. It's doing what comes naturally. This is the tremendous dilemma that people get. Now why? Because atoms are quantized. And we have these spectral lines rather than the continuum. And then the rule that they found was that if you go from E, sorry, I can't see it at the moment because I can't see it. It's EN. Don't worry. I've got your pictures over the top of me. EN to EN. Take the energy difference to give you a frequency. That frequency is the same as the sum of the transition from there to there and the transition from there to there. And we call that the Rydberg combination principle because it works all the time. And if you put this in the exponential multiplication, because it's squared terms that gives you the energy, you add the frequency. And that's why Heisenberg did this. Okay? And that's why.
So when you're squaring them, this again, because they're frequencies, this is the non-commutative secret, is that you have this, the exponential ratios are non-commutative. And that's what it all comes down to, is that because of that exponential phase space, that's the quantum potential that's hidden and that Schrodinger ignored.
It comes out time and time again. Okay, now what Bohm did was to turn this into a structure process. So you can either talk about Q going from N to N, or you can talk about it going intermediate state. So in fact, the actual motion, you have to sum over all these. So the actual underlying process that's going on is more like a fractal. And now you see where the ambiguity is coming in, where your creativity might be coming in. So this is just a statistical average of all these underlying processes. And how about this? Anthony Gormley's brilliant statue. Just the density. And in fact, if you write E is equal to AB, you can split these equations apart, and you can get two Schrodinger equations. Here's one Schrodinger equation I've written with A's instead of sides, and this one is the complex conjugate Schrodinger equation. And I felt very clever when I did this, because I invented it all myself. And then I was reading Paul Dirac's paper in 1930. He actually had exactly the same thing. And he actually talks about folding and unfolding in his book, The Principles of Quantum Theory. He actually has the Bohm theory in his book, Principles of Quantum Theory, in 1947. And I think David got it from there. Anyway, so whether that helps or not, I don't know, but it's not pulled out of the air. Then you have this polar decomposition appearing again. And if you write it in the modern work, I'd like to call this the Brown-Hiley cartouche, if I may, because we tried to publish this equation, and the Phys were not very interested because they didn't understand what we were doing. So trouble refused.
So you have to do this polar decomposition, and that's why you get the momentum as a squaring for the kinetic energy. And that's where you get the Planck's constant squared, that he says that was what was being ignored by Dirac and Feynman.
But this equation is very important because what it enables one to do is to take Bohm's ideas and to deal with spin, and also to deal with relativity. You'll see in a lot of the elementary discussions of the Bohm theory, they can't do relativity. I was going to say something beginning with B then, but I've checked myself. We can do something. And this comes from these two equations. And this is, I've learned something. And this is the commutator that we saw, the order with the difference. And this is called a Jordan product. And I don't think Jordan doesn't get mentioned very often. And there's a problem here, a political problem, because Jordan actually was in the SA, not the SS, but in the SA. And I'll leave that just as that comment. Okay, now how do we get back to the paths again? Well, what we do is we say, okay, it's unfolds, enfolds, unfolds, enfolds. And this is Dirac speaking now, it's not me.
Okay, so I think that gets the message across pretty much. Thanks.